Hello, 112 class. We're going to pick up with the next topic, which is electrolytes. And I think this is in chapter 18. I think that's the right number. They renumbered the chapters on me, but I think that's it. And so in this chapter, one of the best summaries of the chapter is this figure. I copied it right out of your book. Basically, this summarizes our experiment from the lab. And so what we observe here is the first category is things that are non-electrolytes. That literally means does not conduct electricity. By the way, electro, of course, means electricity. And light means sort of to break up. So an electrolyte is literally something that when it breaks up in water will conduct electricity. Okay, so we saw this by plugging in a light bulb to certain solutions. And if it is an electrolyte, it glows. If it's not, it doesn't glow. So non-electrolytes are things that are covalent compounds that are not acids or bases. So in the laboratory demonstration, we used sugar. And when I put sugar in water, it dissolves, but it doesn't conduct electricity. If we also tested ethanol, which is, just alcohol and water, ethanol is this little molecule here. And so they've shown us, like, here's one of them right there. Ethanol dissolves in water because it has an OH bond. So it has hydrogen bonding capabilities. So it'll dissolve in water. But it doesn't ionize because there is no, it's not an acid or a base, and it's not an ionic compound. So anything that doesn't ionize when it dissolves in water is a non-electrolyte. That means it doesn't conduct. On the other hand, something like copper chloride here, CuCl2, when you put that into water, it goes from being a solid like this to breaking apart into its pieces. So here we have a copper 2+ particle, and this one is a chlorine minus. And so when we picture what's going on, as we know from prior chapters with intermolecular forces and solubility and all of that, what we know happens is that the little positively charged copper gets surrounded by water where the oxygen is pointing to it. And the negatively charged chlorine would be, that's this one, would be surrounded by waters with the hydrogen pointing at it because, the hydrogens have a partial positive charge, so they like to align with the negative part of the ion. This would be an example of an ion-dipole interaction. But the fact that we have ions in the solution means that this solution will conduct electricity. And in fact, the more ions you have, the more it will conduct. So we can think of that as more ions equals more light, right? Okay, so strong electrolytes are generally anything that is ionic, and as long as it dissolves in water anyway. Strong acids and strong bases. Now we've mentioned those terms before, but we're going to delve into that a little bit more in a second. Weak electrolytes are things that when you put them in water, occasionally they'll form an ion. So like acetic acid, for example, we saw it as a weak electrolyte. It's not as bright as the copper chloride is. So what that tells us is that acetic acid, when you put it in water, some of it stays as acetic acid, and a few pieces of it, relatively small amount, transform into acetate and hydrogen. So this is an acid, so that means it loses a hydrogen. And when it does that, it leaves behind CH3COO minus. That's acetate. If you forget that, it's called acetate. That name is on the back of your periodic table that I gave you. So acetate ions are charged. So here's an acetate, and it's going to get surrounded by waters with the hydrogen pointing inward because it's a negative particle. And then over here we have hydrogen ion. So the occasional particle, so we see here that, let me change colors here in my pen. we can see that most of the particles with acetic acid are still have their H on it. That's the little end here that looks like a nose of a puppy. So most of the time, acetic acid stays as acetic acid, but occasionally one of them splits apart to be these charged particles. So that means that there's a few ions running around in the solution, so it conducts the electricity a little bit. By the way, the only substances that are weak electrolytes are what we call weak acids or weak bases. That's it. So the name kind of matches: weak electrolyte, weak acid, weak base. Strong electrolytes are either ionic compounds, like this example here, or strong acids and strong bases. Okay. So that means we need to remind ourselves a little bit about what we know about ionic compounds. First off, if an ionic compound is soluble, that means that it will dissolve in water, right? If it is soluble, when you put it into water, so we start off with a solid, when we mix it with water, it always ionizes. So ionizing means that it forms the ions, Na plus and Cl minus in that case, or the copper ions, like from the prior slide. Ionic compounds always do that. So anytime you have an ionic compound that dissolves in water, this always happens, right? You start with a solid and it's going to produce ions. That's what makes it an electrolyte, because we only have the ability to conduct electricity if the particles are charged. If it stayed as NaCl, one solid piece of NaCl, no charge, then it wouldn't conduct. Okay, so then let's think about this. If 1 mole of NaCl is used in the beginning, when it dissolves, we would get, so like 1 mole can be thought of as like 1 particle, right? So if we had 1 particle of NaCl, we would always get 1 particle of Na plus and 1 particle of Cl minus. So the reason that ionic compounds are such strong electrolytes is because basically I get 2, in the case of NaCl, I get 2 moles of ions for every mole of the parent compound I put in. So there's 1 mole of Na, and there's 1 mole of Cl. That's 2 moles of different ions that I can use to move electricity around. Now, the copper chloride is a bit different, because when this ionizes, this Cl2, this is not Cl2 the gas, the element. This is a compound, so that means that the chlorine has to have a charge, like it does right here. So if a particle has a charge, then the coefficient becomes a that was backwards. The subscript becomes the coefficient. So this little 2 down here goes in the front when it ionizes. So that means if I have 1 mole of copper chloride solid, when it dissolves, I have 1 mole of copper ion, because there's 1 copper ion for every copper chloride. But then I have 2 moles of chlorine ion. So that means, this is supposed to say copper. That means I have a total of 3 different moles of particles here to conduct electricity. So that makes it a really good electrolyte. So in either case, we end up with so many particles that are ions that the light bulb is really, really bright. So we call it a strong electrolyte. Okay, so now in the lab, we did an example of where we had HCl, and that was a strong electrolyte. It lit the bulb up completely. The reason for that is that HCl counts as a strong acid, which means that it dissociates completely. Dissociate is a process, like, it literally means to separate. So the hydrogen ion separates from the other part completely. Acids always make hydrogen ion. So here, every mole of HCl I put in results in 1 mole of H plus and 1 mole of Cl minus. So just like the salt was, this NaCl before, we get lots and lots of ions that will conduct electricity. Weak acids are a little bit different. So when we tested the acetic acid, we found that the light bulb doesn't glow as much. So when we did HCl, it's a strong acid. It dissociates completely. So if we had 1 molar HCl, that means we would get 1 molar H plus, because there's 1 hydrogen in our formula here. Acetic acid is a weak acid, which means that it does not dissociate completely. So if I start off with 1 molar acetic acid, it turns out that most of the time acetic acid stays as acetic acid. It doesn't lose the proton all the time. In fact, if we put in 1 molar acetic acid, you would only get 0.004 molar hydrogen ion, and also the same amount of acetate, because if I make a hydrogen ion, I also make an acetate ion. That means that mostly acetic acid stays as the whole molecule, which is not charged, so that doesn't conduct. The only part that does conduct is this total of 0.008 molar ions. So we communicate this kind of a situation where you have the parent compound, acetic acid, and the ions at the same time in solution by using that double-headed arrow like this. Okay, that means that they sort of go back and forth. That's called equilibrium. And we will study that more extensively in a little while, because it is a very important concept. So here's another example. The strong acid we looked at in class in lab was HCl. And so HCl, when you put it in water, separates like this into an H plus and a Cl minus. Those can both conduct electricity. Very, very, very few, almost no particles would remain as HCl together. So we can show that with a double-headed arrow where the reverse reaction is very, very small. On the other hand, HF is a very weak acid. Hydrofluoric acid is very weak. So that means mostly it exists as HF, and sometimes there's a minor amount of ions that form. So if we put HF into our light bulb, it would faintly glow, just sort of like the acetic acid did. It's a weak electrolyte. Now, that does not mean that hydrofluoric acid is safe by any stretch of the imagination. Hydrofluoric acid is actually one of the most dangerous things, and to purchase it, you have to have a permit from the state and the federal government that takes about 12 weeks to get. And the way it's packaged is very, very particular. It can't be put into glass or metal or most plastics, because it will literally dissolve it. HCl can be put into glass and several other kinds of plastic with very little harm. So just because we use the term weak acid, that does not mean it is not reactive. It just means that it exists mostly as the whole particle HF rather than as ions. So the term weak doesn't mean not reactive, it just means that it conducts less electricity. We can rank different acids and bases by how strong they are. So we said HCl is a strong acid, meaning it dissociates completely. There's about 6 other strong acids. This figure only has 3 of them, but they're the 3 most common. So hydrochloric acid, sulfuric acid, and nitric acid are the most common strong acids. And when they give up an H, they would form what we call their conjugate. Conjugate means like opposite or pair. So HCl would make the conjugate Cl minus. Now, since HCl is such a strong acid, its conjugate is really a bad base. So we call it negligible. Negligible meaning not good. So if you have a strong acid, once it's lost the proton, it stays that way. It doesn't go backwards. On the other hand, for this area where it says weak acids, these, like HF, once they give up their proton, they can go back the other way, because the ion that it makes is a good base. It's a weak base, so it can go back and forth. So this middle part is all equilibrium arrows, and the top part And the bottom part on this left, on the right, where the bases are one-way arrows. So just one way. Okay.